In this example, we're told that we have a dryer and we're trying to find the flow rate through this flexible metal pipe that leads from the back of the dryer out into the outdoors. We're told that this flexible pipe diameter is 4 inches in diameter. It's galvanized iron vent. We're not to have more than 20 feet of pipe and 4 90-degree elbows. And under those conditions, we're asked to find the air flow rate if the gauge pressure is given as just over 1 pound per square foot. And then we're also given some information about the air properties and the loss coefficients. So let's go ahead and analyze this. This will be a type 2 pipe system problem because we're trying to find the air flow rate. So we don't know the air velocity in this pipe. And because we don't know that, we don't know the Reynolds number, so we can't find the friction factor easily. So we're going to probably have to do some iteration in this problem. So let's first of all sketch out the problem schematically. So this is our dryer. And then I'll just draw kind of the worst case scenario for the pipe with our 4 elbows. And we'll discharge into the atmosphere here. So we have our 4 elbows in the diagram. I'm not going to worry about changes in elevation like over in here because when you're dealing with gases, the potential energy term in the extended Bernoulli equation is really small compared to the other terms. So I'm not going to worry about elevation changes. They'll be negligible. So let's go ahead and apply the extended Bernoulli equation between 2 points. So point 1 is going to be in the dryer. Then there's some stream tube that goes here. And I'm going to make my point 2 right here at the exit of the pipe, right at the exit. Now by putting it point 2 right at the exit, I know that the pressure there will be the same as the surrounding atmosphere because it'll be a free jet. But I don't have any loss coefficient there because the velocity of the fluid right at point 2 there is still the same velocity as in the pipe. I could have put point 2 prime out here where the velocity is basically 0. Again, the velocity here, the average velocity at point 2 here is still the velocity in the pipe. So there's no loss coefficient. But out here at 2 prime, the velocity is 0. So 2 prime, to get to there would be an exit loss. You can work it either way. You'll get the same result. But for me working it out here, I'm going to just choose my point 2 there. So let's go ahead and write out the extended Bernoulli equation. And then we'll simplify it based on the information that we know. Okay, so here's the extended Bernoulli equation. Let's write out some of the information we know. We know that the gauge pressure at point 1 is given. This is 1.04 pounds force per square foot gauge. Since we have a gauge pressure there, then we should make the pressure at 2 also gauge, so that'll be 0, just gauge pressure. The velocity at 1 will be about equal to 0. So it's the velocity here inside the dryer. Now, of course, the dryer's tumbling and there is some air velocity in here, but it's small and it's not really coordinated. It's not directed in one particular direction. It's just sort of random. So over some period of time, if you average the air velocity inside the dryer, it would be about 0 when you kind of factor in the directions and such. Certainly it's small compared to the velocity in the pipe there at 2. So we're going to assume the velocity at 1 is 0. The velocity at 2 will be the same velocity as in the pipe because I put my point 2 right at the exit there. Now, the elevation differences, Z2 minus Z1, we're going to say are about 0. We're going to neglect those because, again, we're dealing with a gas. We don't have to really worry so much about elevation differences. The shaft head between 1 and 2 is 0 because we're assuming that there's no pump or turbine or anything between points 1 and 2 here. The reason that we have flow between 1 and 2 is just because point 1 has a higher pressure than point 2, so it's just pushing the fluid through here. Now the head losses between points 1 and 2, let me write that down here, will include an entrance loss right there. So there's a minor loss there. Then we have 4 elbows. Those are also minor losses. And then we have a major loss as well. So let's write down all of those. So let's write the major loss first. So here's our major loss. Got the friction factor. This is the Darcy friction factor times the length of the pipe divided by the pipe diameter. This is the velocity in the pipe. And then the velocity squared over 2g is the velocity head there. So that's your major loss. And then our minor losses, we'll have an entrance loss. And the correct velocity head there will be based on the pipe velocity. We also have 4 elbow losses. Those all occur within the pipe as well. And then that's it. There's no exit loss because I've chosen my point 2 to be right at the very edge of the exit there. So the velocity at 2 is still the same, the velocity in the pipe. If I used point 2 prime, then what would be different in this problem would be the velocity at 2 prime would be 0, and then we would also have an exit loss that we would have to add in. You'll get the same result in the end, but it's just kind of shifting where some terms are. Okay, so we're going to just keep our point 2 right there. All right, so let's go ahead and substitute into our extended Bernoulli equation and simplify things. So you'll see that what we have, let me just go ahead and write this out. We'll have the pressure at 1 in terms of the gauge pressure all over rho g. That's going to be this term here. And then I'll bring this head loss term over to the left-hand side and combine it with the velocity head term here. Oh, one other thing. I need to know something about the kinetic energy correction factor. So I'm going to assume at the moment, this will be a turbulent flow. So I'm going to assume that the kinetic energy correction factor at point 2 is equal to 1. So I'm assuming it's turbulent. The reason I'm assuming that is because it's a pretty large diameter pipe. Keep in mind that this is like a 4-inch diameter pipe. So I'm expecting the Reynolds number to be relatively large. So I'm assuming it to be turbulent. I'm going to have to check that assumption at the end of the problem. If it's not turbulent, then I need to come back and rework this assuming that it's laminar. Okay, but for now, let me assume it's turbulent. I'll check my assumption, and if it is turbulent, then everything was okay, and I'm just fine. If it's not, then I'd have to rework the problem, assuming it's laminar. Okay, so anyway, keeping that in mind, and bringing the head loss term over to the left-hand side, I'm going to get the following. So there we go. So these terms here, here's our major loss. These are our minor losses, and this plus 1 is because of the velocity at 2. So that's what that plus 1 comes from. All right, so our next step is to start plugging in the numbers that we know. So what we're ultimately trying to find here, by the way, is the velocity in the pipe. We're trying to get the volumetric flow rate through the pipe, which is really connected to the velocity in the pipe. We know the gauge pressure at 1, right? That was given as the 1.04 pounds force per square foot. So we know that information. We know the density of air, 1.23 kilograms per cubic meter. Of course, we know gravity. It's 9.81 meters per second squared. We know the length of the pipe is, I think we were told it's 20 feet. Let me just double check that. Yeah, 20 feet of pipe. And we also know that the pipe diameter is 4 inches. We know the entrance loss that was given up here of 0.5. We also know the elbow losses. These are all just sort of approximate numbers. And I think that's pretty much all we have given. Yeah, I believe that's it. Now, I have some mixed units here. You can see these are in metric, these are in English units. So you'd have to do some unit conversions. I'm not going to do those here just for the sake of time, but you'd have to do some unit conversions for all that. If you do all of that and kind of simplify things down, you'll get the following expression. You'll get the velocity and the average velocity in the pipe squared times 60 times the friction factor plus 7.5 equals 945.5 feet squared per second squared. So the one thing that we don't know in this equation up here is we don't know the friction factor. And the reason we don't know that is because we don't know the Reynolds number for the flow. Oh, by the way, one thing that we do also know is the relative roughness of the pipe. So we know the roughness of the pipe itself. That will end up being 0.0005 feet. Oops, let me fix that. And that's because we're dealing with galvanized iron. So that came from a table, just looking up the roughness for a particular pipe. This, again, is very, very rough because, in fact, this is probably not a terribly accurate number because these kind of dryer vents have quite a bit of roughness because of the flexibility of them. Galvanized iron pipe like this is more for like pipe you might have in kind of wastewater handling in your residential construction in old homes. So this is not quite the right roughness for what we'd have here, but I'm going to use it anyway because that's really all we have in our tables. So let's go ahead and just stick with that value. So we do know our relative roughness because we can calculate epsilon over d to get the relative roughness. All right, so now we have this expression down here from our extended Bernoulli equation. It's just basically simplifying the extended Bernoulli equation and then plugging in our numbers. But we can't solve for this velocity in the pipe because we don't know the friction factor. And the reason we don't know our friction factor is because we don't know the Reynolds number in the pipe. And in fact, if we calculate the Reynolds number based on the pipe diameter, it'll be the velocity in the pipe times the diameter of the pipe divided by the kinematic viscosity of air. If I go ahead and plug in the numbers that I'm given for the kinematic viscosity of air and the diameter of the pipe, we'll end up getting the Reynolds number looking like this. Okay, so let me just underline the important equations here. We've got our extended Bernoulli equation here. We've got our Reynolds number relation underneath it. And our relative roughness, which we're going to use to find the friction factor, that comes out to be 0.0015. Okay. So now we need to figure out how to find our friction factor since we don't really know. We don't know our velocity, so we can't calculate our Reynolds number. And if we can't calculate our Reynolds number, we can't find our friction factor, which means we can't find our velocity. So how are we going to find that velocity? Well, the approach we're going to take is we're going to do an iterative approach. And let me just kind of sketch it out for you. So iterate to find the velocity in the pipe. And the approach I'm going to take is I'm going to just choose a value for the friction factor, a reasonable value. Okay, so if I go to my Moody plot, I can certainly, in fact, unfortunately I don't have a Moody plot on this page, but let me sketch it out. So if you look at the Moody plot, it looks something like this. Here's the Reynolds number. Here's your friction factor. Here's your relative roughness over on this side. And you have these plots that look like this, these curves that look like the following. So what I'm going to do is I'm going to choose a reasonable guess for the friction factor. And the way I'm going to do that is I know my relative roughness up here, 0.0015. So I'm going to just go over here and find 0.0015. Let's find the line that corresponds to that. Let's say it's this line. And I'm just going to go straight across. I'm going to start in my fully rough zone. Remember that there's a line here that looks like this, where up above this line, it's in the wholly turbulent zone where these lines are almost horizontal. I didn't do a good job drawing it here, but they're nearly horizontal on the Moody plot. So I'm going to start with that value and then just come over and read off what the friction factor is on that. So I'm just kind of starting by saying that we have a really large Reynolds number. That's my initial guess, and use that for my friction factor. Okay, so that's going to be my first guess. And then step 2, once I know that, now I can find the velocity using the extended Bernoulli equation. Which is this equation right up here. Okay, so I'm going to use this equation. So now I've guessed my friction factor. I can solve for the velocity in the pipe. All right? And then step 3 will be to calculate the Reynolds number. Using the velocity in the pipe that I just found. So now that I have the velocity in the pipe, I can come to here and calculate the Reynolds number. Right? Because I know the velocity in my pipe, I'm going to substitute in, find the Reynolds number. And now that I know the Reynolds number, I can go back to my Moody plot. So use Moody plot to find my friction factor using my given Reynolds number and the relative roughness. So now that I have my Reynolds number from step 3, I can use that Reynolds number and the relative roughness to find the friction factor. So let's just pretend for a moment here that my Reynolds number is right here. Or let me put it in a different location. Let's say my Reynolds number is right here. Okay, the one that I get from step 3. And then what I would do, oops, that looks bad. Let me try that again. So what we would do is we would go up, see where it intersects with our relative roughness curve, and then come over and read off the friction factor. And in this particular case, you'll see that my initial friction factor and the current friction factor are different from one another. So then if they're different, then I need to start the process over again. So this will be my step 5 is, let's call this step 4 friction factor, let's call it F prime. Is F prime equal to F? So in other words, is this friction factor that I'm finding at step 4 the same as what I guessed in step 1? So if it's yes, then I'm finished. Everything is now consistent. I've guessed the correct friction factor, everything's done. But if it's no, then go back to step 2 using the new F prime. So what I mean by that is, so now I'm in step 5. My original friction factor, which was the blue value here, is different from my orange one. So they're different. So then I'm going to go back to step 2 using the new F prime. So this orange friction factor, I will now use in my extended Bernoulli equation right up here. I'll use the new F prime here and then solve for the new velocity. And then use that velocity to find the Reynolds number, and I'll go back to the Moody plot and find an F double prime using my new Reynolds number and relative roughness. And then just keep iterating through this until it eventually converges to until the two friction factors are the same. And typically this will converge. So in fact, following that procedure, here are the values that I got. So I assumed from the wholly rough turbulent assumption that the friction factor was 0.025 in my very first iteration. So that gave me the velocity in the pipe of 10.25 feet per second, solving the extended Bernoulli equation. That gave me a Reynolds number of 19,000, which then gave me a new friction factor of 0.029. So you can see that this friction factor from the Moody plot's a little different from what I initially guessed, so I need to iterate again. So with my new friction factor of 0.029, calculate the velocity in the pipe. That comes out to be 10.11 feet per second from the extended Bernoulli equation. The Reynolds number corresponding to that comes out to be 18,800. And then from the Moody plot, my new F prime comes out to be 0.029 in that case. So now those two are equal, so I'm finished. So I don't need to iterate any longer. So that would mean that the velocity in the pipe is now 10.11 feet per second. And if I want the volumetric flow rate, That'll just be the average velocity in the pipe times the pipe diameter. I'm sorry, the pipe cross-sectional area, I should have said. And we can go ahead and calculate that out. That'll come out to be 0.882 cubic feet per second, which is what we were asked to find. So that's how you do this kind of type 2 pipe system iterative approach. Now, let me just say a few words about the iterative technique I used here. When you do iteration defined velocities and such, there's more than one way to do it. This is just the way I chose to do it because it makes a lot of sense to me, but you may come up with another approach to iterating to a solution, which is fine. Okay, they don't all have to be the same iterative approaches. This is just my algorithm that I came up with. The thing about iterative techniques is you're not always guaranteed that you're going to iterate into a solution. So in this case, it iterated pretty quickly, but it's possible that your iterative scheme may not actually converge to a solution. So that's unfortunate, but that's just the way life is. If you have a reasonable first guess for the friction factor in this scheme, then it will converge pretty quickly. It's possible if I had a terrible first guess, I might not actually converge. I'm not really sure. I haven't really tested it here, but with iterative schemes, you're not always guaranteed. One way to think about that is if you go back, I don't know if you've had experience with the Newton-Raphson method for iterating to a solution in root solving for equations, but there are some conditions under which that Newton-Raphson technique will not converge. So it's possible that we may run into a situation where it doesn't converge. If you come across a situation like that, first thing you ought to do is try a different initial guess to see if you can get it to converge for a different guess. Very likely when you solve these pipe system problems, you're not going to run into those problems, but I just want you to be aware of it. So it's possible to have a different iterative scheme. It's possible that your iterative scheme may not converge. Most likely it will. The very last thing I'll say is it helps to have a good first guess in these kinds of problems. So, I made my first guess here just using the wholly turbulent zone for my friction factor. That's a very reasonable first guess, and it seemed to work pretty well. In fact, I only had to do 2 iterations, and I found my answer. So use a reasonable first guess. Don't use a friction factor of 1,000,000 or 1 times 10 to the minus 8 as your initial first guess. That's a terrible first guess. Choose something that's in the ballpark of what the answer will likely be, and that'll really help you out. One other thing I forgot to do here, or at least forgot to mention, is recall up here I assumed that the flow in the pipe at the exit was going to be turbulent. I should just verify that that assumption is correct. And if you'll notice back down here, when I calculated the Reynolds number for my final state, I'm over that, I'm at almost 19,000. Recall that the Reynolds number, critical Reynolds number for flow in a circular pipe is 2,300. So since my Reynolds number is greater than 2,300, I have indeed turbulent flow in the pipe. So my assumption is correct that, I assumed it was going to be a turbulent flow, and indeed it is. So it's always a good idea to just go back and double check any assumptions you make to make sure it's all consistent. If I found out that that was an incorrect assumption, let's say my Reynolds number here was 1,000, and in fact it was laminar, then I'd have to actually start the problem over again and assume that alpha was equal to 2, assuming it was laminar, and then work out the problem that way. Okay, so that's just another thing to keep in mind. Okay, so this was a good example involving a type 2 pipe system problem, one where you have to iterate to find a velocity or a flow rate. We'll go ahead and end there.